All right, this is the final lesson of Unit 5. This is U5L5, which is testing a claim about a proportion. This will go really quick because this is just like our L2 notes, because if you remember in L2, we did a proportion problem. So we're going to get right into it. Same steps we've had on every problem that we've done in this unit, basically, since L2. We find our hypotheses, we set the significance level, we find the test statistic, find the p-value, make a conclusion, and then state that conclusion in non-technical terms. Okay, so we're going to go after this XSort method problem. Okay, so the XSort method is a method of gender selection that promises couples an increased chance of having a baby girl. Among 726 babies born, so this is our evidence. Among 726 babies born to couples using the XSort method in an attempt to have a baby girl, 668 of the babies were girls and the others were boys. That's our evidence. Use these results with a 0.05 significance level to test the claim, so 0.05, that among babies born to couples with the XSort method, the proportion of girls is greater than, so this is the claim, test the claim. The claim is that the proportion of girls is greater than the value of 0.5 that's expected with no treatment. Okay, so there's the claim that this XSort method is going to make the proportion of girls, the percentage of babies that are girls, be greater than 0.5. So our null hypothesis is that the proportion, so we're talking about proportion, so it's going to be P. The proportion should be the normal, 0.5, 50% of the babies will be girls. And the alternative hypothesis is that the proportion is going to be greater, because of this wording right here, greater than. It's going to be greater than that 0.5 that we would normally expect. Significance level was given in this problem to be 0.05. So we know that alpha equals 0.05. This is the test statistic we're going to use. We saw that in L2. This is z equals p hat minus p over the square root of pq over n. Remember, p hat is from the evidence. P and q are from the hypotheses. Okay, so we're going to have z equals, we need a p hat here. Well, p hat came from the evidence. The evidence said 726 of the 668, out of 726, 668 were girls. Okay, so 668, I can write this off to the side here. P hat equals 668 out of 726. Because that's such a big fraction, I don't mind changing that to a decimal. It'd probably be easier to work with as a decimal. So 668 divided by 726, my calculator tells me that that's 0.92. It's really 0.920, but I'll just leave it at 0.92. Okay? Now, from the hypotheses, our P is 0.5. Well, if P is 0.5, Q is also 0.5. So we know our P's and Q's, and then our N is always going to be the bottom of that fraction because it's just how many total subjects there were, how many babies. Our N is 726. So all of this information can now get plugged into this formula. P hat is 0.92 minus P, which is 0.5, divided by the square root of PQ, which would be 0.5 times 0.5, divided by n, which is 726. And we're going to use that to find our z. So I go to my calculator, parentheses around the 0.92 minus 0.5, divided by big square root here, 0.5 times 0.5 divided by 726. I'm going to get a crazy high z-score, 22.6. And remember this, or 22.63. Remember, this is z, which we know really confidently 10 can be treated as infinity. So this z is actually way past infinity. You're going to get a weird answer if you try to calculate this or type this into your calculator. So I'm just going to kind of draw the picture here and say, well, 22.63 is way over here. I know I'm drawing it in a way where it looks like there's some shading, but it's so far past 10, we can actually call this p-value 0 plus. The actual shading here would be really low. Like even if you went to your calculator and you try to do normal CDF, which is what we would normally do, normal CDF, and we're going to the right because it was a greater than, so 22.63. We can't put 10 because 22.63 is bigger than 10, so 10 can't be the right bound. So let's use an obnoxiously large infinity example. Let's do 9999 like I did in the last notes, and then 0 and 1 like we always do for normal CDF. If we do that, I'm not even sure our calculator is going to give us an answer back. Let me check. I'm going to put in 22.63, comma 999901. My calculator just calls it 0. It's such a low probability, our calculator can't even communicate it to us. So it's 0 plus, which for all functional purposes, we can just treat as 0. And what that means is we're going to be able to reject no matter what alpha is. We are certain that this shouldn't have happened. If the real probability of having a girl is 0.5, there's no way we're getting 668 girls out of 726 births. Okay, so we go to our conclusion. 0 is obviously less than no matter what we set alpha to be. I think we set alpha to be 0.05. 0 is definitely less than that, so we will reject the null. We always reject if we are less than the alpha. So we will reject the null. And our conclusion is there is definitely enough evidence. There's enough evidence to show that this method increases the probability of having a baby girl. I forgot to mention at the 0.05 significance level, you can't go back once you've already collected the evidence, everything, and be like, oh, well, let's call it the 0.01 significance level just because we're so sure. We decided at the beginning of this problem it was a 0.05, so it'll be a 0.05 all the way to the end. But with this evidence, there's no way we're wrong in making this conclusion. This method really works. So one more problem, putting it all together. This is our last regular example here in our notes. Okay, a recent study showed 53% of college applications were submitted online. Assume that this result is based on a simple random sample of 1,000 college applications, 515 submitted online. Use a 0.01 significance level test to test the claim that among all college applications, the percentage submitted online is equal to 50%. Okay, so there's a lot of numbers going on in here. Let's look at what's actually being said. The claim at the 0.01 significance level is that the percentage that's online is equal to 50%. That's the claim. So let's focus on that because that gives us our hypotheses. Our null hypothesis will be that the proportion, so we're talking about percentages, so this must be a proportion problem, not a mean problem. So we're using P, not mu. P equals 0.5, that's 50%. And they don't say greater than or less than, so it's a not equal to problem. So our alternative hypothesis is P does not equal 0.5. Significance level was 0.01. So I know they're saying something up here about 53%, okay? But the evidence I actually have here, evidence-wise, is that out of 1,000 applications, 515 are submitted online. That's my real evidence. So let's not worry about what they're talking about up here. Let's worry about what's going on in the evidence. Okay, the evidence is where we're going to get our p hat, and that shows 515 out of 1,000. So I'm not sure where they're getting this 53% from, but let's focus on the actual evidence we have. So because it's a proportion problem, we're going to use z equals, and I'll go up and look at my notes from earlier because I need this, p hat minus p divided by the square root of pq over n. So p hat is going to come from this 515 out of 1,000. So I got to find somewhere to put that information. I'm just going to write it up here. P hat equals 515 divided by 1,000, which is 0.515. if you type it into your calculator. So that's my p hat. So we're going to have z equals 0.515 minus the p from the hypotheses is 0.5 divided by the square root of that same p, 0.5. Q, if p is 0.5, q is 0.5. Remember, you find q by just doing 1 minus p. So this is also 0.5, and our sample size is 1,000 here. What you'll notice is the larger your sample size, the easier it is to make conclusions, the more likely you are to reject if they're different at all. So let's see, 0.515, I'm going to put that in parentheses, minus 0.5 divided by the square root of 0.5 times 0.5 divided by 1,000. And I'm getting a z-score of 0.949. So this one actually might not end up being a rejection, okay, even though we have a large sample size of 1,000. We have 0.949. Okay, so next step, so I found my hypothesis, significance level, test statistic. Next step is the p-val. Well, this was a not equals to problem. So we're going to go, if it's positive, we'll go to the right and multiply by 2. If it's negative, we'll go to the left and multiply by 2. This is positive. So we're going to go to the right and multiply by 2. So we're going to have normal CDF. Going to the right means we're going to start at the z-score, 0.949, and we're going to go up to infinity, which would be 10, comma 0, comma 1. If you need to draw a picture for that, this is how it looks. 0.949 is over here, and we're shading to the right. So we're going up until infinity, which we call 10. And then we're going to have to multiply by 2. Whenever we have a not equals to problem, we go to the right if it's positive and multiply by 2, or we go to the left if it's negative and multiply by 2. So I go to my calculator, second distribution, normal CDF, 0.949, comma 10, comma 0, comma 1. I'm going to multiply that by 2, and I get an answer back of 0.343. That's my p-val. And now finally, I'll make my conclusion. 0.343 is not less than or equal to 0.05, or 0.01 was our significance level here. It's definitely not, so we're going to fail to reject the null, which means there's not enough evidence at the 0.01 significance level to say that 50% is not, we're going to use the term not because it was a not equal to problem, and we're always talking about the alternative hypothesis, is not the percentage of applications that are submitted online. Okay, so the original claim was talking about it being equal, but the actual hypotheses say not equal to for the alternative, and that's what we care about. So we say there's not enough evidence to say the alternative is true. There's not enough evidence to say that 50% is the percentage, or that 50% is not the percentage of applications that are submitted online. And that's it. We're through all the notes for this chapter. Now